right, hey everyone. Just a quick reminder that Geek Movie Night is tonight at 6 o'clock right here. And if you have not, if you want to come and you have not RSVP'd, well, number one, why didn't you? But number two, you should still come because we did get some extra pizza. So if you forgot to RSVP, please still come. So the movie, just as a reminder, is For All Mankind, which is a documentary about the Apollo mission, so should be good. Okay, our first speaker is Joshua Garcia Sheridan. He is a first-year graduate student studying power electronics under Professor Plawa. He completed his BS degree in electrical engineering in spring 2013 at UIUC, and his primary research interests is in renewable energy applications and compact power electronics.
Okay, can everyone hear me? All right. So yeah, hello everyone. My name is Joshua Garcia, and I'm here to present the basis of my research in submodule control of a multi-level DC to DC converter for solar photovoltaic applications. So I will be going over fundamentals of solar photovoltaics, battery charging, and combining the two to create a solar photovoltaic battery charger circuit. And then I will be considering design for highly efficient and compact design for battery charging. I'll be considering recent works in differential power processing and DC optimizers in that process, choosing DC optimizers ultimately, and identifying the critical benefits I get from that. And then I'll also be talking about the application, the approach. In practice, looking at circuit hardware techniques that are founded for the actual hardware I'll be using to conduct my research in. And I will be then describing the control challenge that my research is going to try to address. So solar photovoltaics are simple in operation. You have sunlight shining down on a solar panel, and you're able to extract DC power from that. For solar panels and any particular insolation amount, you will have a maximum power point, and this is the power point. This operating point is the ideal point to operate your solar panels at all times. That way, you get the most energy from it. And we want to apply this to battery charging in particular. In battery charging, especially for instance, lithium-ion batteries, which are commonly used today. You have to charge the battery at a particular fixed voltage that is dictated by the state of charge. So for instance, in a graphite anode-based lithium-ion battery, you'll have a generally flat curve, maybe varying between 4 and 3.5 volts for state of charges above 20%. So we want to work with photovoltaics to charge batteries because photovoltaics are quite convenient in mobile applications. For instance, UAVs, you can apply full solar panels on top of the wings, as you can see in this image here. We have the Raven, a UAV for reconnaissance use. And also solar panels are even used in some very simple devices today for phone charging, tablet charging, and even some EV applications, for instance. The main thing that I want to take from this, however, is that a major design consideration for a solar charger is that we often work with curved surfaces on things like UAVs, and so because these curved surfaces, which are naturally needed for aerodynamic efficiency on a plane powered by solar as such, you end up seeing insulation differences across a solar panel that way, across the whole solar system. You basically get a gradient of insulation, and so that introduces mismatch, and that's something that we want to address. In a typical, and probably the most basic sort of PV charging circuit, you'll have a single converter stage, DC to DC, monitoring between the fixed voltage of the battery that you're trying to charge at, and the optimal point, the optimal maximum power point of the solar panel. So we're using MPPT to deliver that maximum power to the battery, injecting as much current as we can at a time. But with a single converter like this, the converter will have to be large in order to be efficient enough for our desire. So this is a very simple system, but it is hardly optimum. So the major obstacles we then face are, we want to have high efficiency, but we want our converter to be rather small. We want it to have low weight, because UAVs don't need any of the extra weight that we're going to be putting on there as a result of having a power stage like that. And we also want to remain extracting the greatest power yield possible. And in the configuration of an entire panel, which is composed of subpanels that we can access, we can do better than just having a single regulation stage across the entire panel. We can regulate each of these individual subpanels to get more power yield, to get more energy yield from it. So let us consider two different architectures that are researched locally around here. Differential power processing is a highly efficient process, because it only requires the processing of a portion of the power that is actually going to be end up going to the output. This is very useful for grid-tied systems, especially because you end up feeding into a centralized DC to AC conversion stage, anyways, and so your efficiency in that case is definitely wanted, something like that. But for a case like mobile charging, we do have to end up using an extra DC to DC stage, because the differential power processing will only regulate this entire subpanel system to be the optimal voltage of the solar panel, therefore not necessarily matching the fixed battery voltage. So instead, let us also consider the DC optimizer system. In a DC optimizer system, each of the individual panels is now being regulated by a smaller unit of DC to DC conversion. In our case, let's consider the buck circuit. In this case, while these three blocks may ultimately be a little bit larger than say the DPP solution here, when we consider that we still need to have a single high efficiency DC to DC stage after that, this ends up the DC optimizer solution ends up being much smaller than that. So for this topology, we get significant benefits of in a series connection, such as what we're showing here for our DC optimizer solution. Each of the output capacitors and the input capacitors will experience lower voltages at each stage, and we can operate these at higher frequencies, because we'll be able to use MOSFETs, for instance. And so with that, we end up with smaller size components with lower voltage ratings, lower necessity for large farad values or Henry values. And we can, furthermore, because we're using a multi-level converter topology, we can implement interleaving. What interleaving does is that we can select a particular some particular harmonic content from, say, from output ripple, whether we're talking about current or voltage, and we can phase shift the switching operation of each of these three converter levels, in order to basically we can at the very best we can cancel out completely some of the harmonic content, and so this drastically reduces the necessary size of especially inductors in the case of current. So ultimately, yeah, even lower size, because this is what the multi-level topology allows us to do. So now let me talk about how in particular the hardware that I will be using for my research is going to accomplish this particular function, performing interleaving by phase shifting the switching operation. I'm using a microcontroller called the it's an Atmel chip called the 1890 PWM316. It has three 12-bit power stage controllers, which output a PWM signal to MOSFETs. And it also features two timer counters with output compare registers that are able to generate interrupts. How this works is in the actual implementation, in our case, we have a particular clock called timer 1. Timer 1 is fed into logic, and so each pulse from that timer is counted in a register. What we can have our code do when we program the microcontroller is set values in output compare registers to compare with this counter value. And so, for instance, if you have all your power stage controllers off at that moment, and you start the first one, and you immediately start this count, then you can basically delay when you turn on the second and third stages. When the comparison between either of these two values and the counter is reached such that they match, then a bit is set in the interrupt flag register for this particular timer counter system that triggers interrupts. And in that interrupt, we can activate the second and third stages of the system. So another feature about the system is that because it is multi-level and we're going to be having this topology work in series, what you end up having happen is that the ground level for every individual converter is going to depend on the output voltage of the previous stage, of the lower level stage. And so we need to level shift signals coming from the microcontroller, which is referred to a particular ground in order to communicate with the other stages. And we accomplish that with ground level translators, which are Maxim chips. So yeah, the converter stages are operating at different ground references. I can show this clearly by noting that we'll have a particular voltage across this zone here. And so then that voltage is translated to this ground level right here, where we have our MOSFETs referring to. So in the example of we have converter 1 with a 12 volt output, just considering it, then that means that the ground level of the second converter is going to be at 12 volts above the reference ground. And if we have our microcontroller connected, as we actually do in the hardware implementation, we have our microcontroller connected to the lowest ground possible, and then it's being fed 5 volts. And so its signals that it's sending out, the PWM signals from its power stage controllers, are only gonna be able to hit 5 volts. I can't program this microcontroller to create a 12 to 17 volt signal for my second stage. So the Maxim chip will be able to basically translate that ground reference level for my signal and make it useful for the second converter. Okay, so then here's another demonstration about what exactly my hardware is able to do. This is a basic per converter graph of my efficiency based upon my output power. And so you see for values above, say, 40 watts, we have about 97% efficiency for these converters. And also I have specifications. This converter set is going to be made to operate at 100 kilohertz with nominal efficiency of 97%, and it is able to take in 7 to 16 volts at the input, which is something that you can find in many sub panels in solar PV. And then output voltage, we can go anywhere from 0.4 to 14 volts. So again, talking about the efficiency. I found these efficiencies by using Python code on a computer to communicate with a power supply, an electronic load, and a set of multimeters, which I connected in such a way that simply I'm providing one stage with a 12 volt source, and then I have the stage programmed to output at 11 volts to an electronic load, and so then I have so the code will set the voltage of the power supply, and it will and by having the electronic load operating in constant current mode, it will increment that constant current up through a desired current range, and then data is taken from the multimeters at steady state. So the code waits for about 5 seconds, and then it'll read the multimeters, and then maybe 10 seconds in, it will increment the current. And so let's see. So finally, let me talk about what my research is actually going to be doing with all this hardware, with all these techniques. In previous works, the maximum power point was tracked based upon a fixed string current, for instance. And so you have perturbed and observed made to maximize voltage for a particular operating current going through the series configuration. In this case, while we're still in series configuration, we want to ultimately regulate to a fixed voltage, and so that changes how we have to control each of these sub-panel systems. And so to begin with, we're going to perform this with a central controller. In this case, we're going to be using the single microcontroller, the 1890 PWM 316. And then later on in our investigation, we'll attempt to scale the system and look at how we accomplish the same thing in a distributed control environment with many scalings of subpanels and so on. And preferably, we want to try to accomplish this with no communication between modules. And so that is the end of my presentation. Any questions? Yes, Enver.
The efficiency curve that you showed, level shifting circuit, or
the question was, does my efficiency curve include what happens when I level shift? As a matter of fact, this one does not. However, when compared with the level shifted efficiencies, which I did do, but I simply have not displayed here, the curves for the second and third stages, which do level shifting, are not different, not significantly different at all in that case.
Is there a reason why you want to
The max. I did not choose the Maxim chip. That is a revision made by Marcel Schuck. I can. This particular revision of the board was designed by Marcel. It was probably an extension of what he had been doing for his thesis.
in the end, it turned out that was a single chip solution that was actually more compact than having an extra diode, capacitor, resistor, and so it turned out to be
That's true.
more compact. And price wasn't as important here, it turned out.
Yep. Just reduce the size further. As you can see, I mean, each of these converter stages is almost like the same size as a penny, and I can assure you that the inductors are sized well enough so that this entire white outline that you see around here, that's the entire working portion of the converter. Flux interleaving? That would be a cool thing to do. It's not necessarily the focus of my research, but it could definitely help.
And then we'll use flux capacitors after that.
Yep. Yes, Chris.
What was the difference in the efficiency curves?
The difference in the efficiency curves
Converter 1, I think, is
for level shifting and non-level shifting, or?
there's converters 2 and 3 are overlaid. Converter 1.
Yes, you're right. Converter 1 is what's providing the 5-volt source to the microcontroller, and so it naturally and that also is extending to the level shifting is done in reference to converter 1, and so each of the maximum chips is also being powered by that converter as well. So in this case, I think I don't believe the level shifting is incurring any loss, because this is the non-level shifted version. But yeah, the microcontroller power consumption is significant to this extent. Ultimately, they flatten out to be almost the same at the higher output power levels, though. All right. Thank you again, everyone.
All right, our second speaker today is Dipanjan Das. Dipanjan is currently pursuing a MS in electrical engineering, and he got his undergrad he got an undergrad in or a Bachelor of Technology degree from Indian Institute of Technology, Kharagpur, with major in electrical engineering. His advisor now is Professor Philip Krein, and his research interests are power electronics, and he's currently working on the power management of stacked system of processors.
Thank you, Saving, for the introduction. My name is Dipanjan, and I am presently working on voltage regulation of series stacked system of processors, or any CMOS circuits for that particular matter. Okay, so this is the basic outline of my presentation today. First, I will be speaking about the present situation of power management of multi-core processors, and after that, how I will talk about how CD stacking of the cores is going to help with all the efficiency considerations or the transient requirement considerations, and then differential power processing, which has already been shown as one of the very important or most efficient ways to series stack some DC systems. And then I'm going to go over the dynamics a bit and what happens when we increase the number of cores, and then we will move on to some other possibilities that help in improvement of dynamics. Okay, so CMOS circuits have been around for like almost a few decades right now. So for the transistor sizes are decreasing continuously according to Moore's law. So consequently, the voltage requirements of each of the transistors at the at the DC voltage rail voltage level is also decreasing. Right now, for example, at 2014, we can see that we are already at 0.84 volts DC voltage requirement. So that is very low compared to what we used to handle before, and that causes a problem with power supply management. First of all, because we have to use synchronous converters, and secondly, as the number of cores are increasing, we have like the basic power that each of the processors are consuming, that remains almost constant. So with decrease in voltage, we also observe an increase in current requirements of each of the processors. So the transient requirements are pretty high. For example, at 0.8 volts, we can have a transient requirement of like 50 amperes, in a step kind of fashion, like in 1 nanosecond it can go up to 50 amperes current requirement. So we have to make our power supply circuit capable of handling such transient requirements. And most importantly, now the research is going on sub-threshold operation of CMOS circuits, which is basically, for example, we have like 0.84 volts of DC rail voltage, but we want to, for efficiency maximization, we want to operate at a sub-threshold level because it gives us, mainly because the power consumption is proportional to VDD squared. So we obtain some kind of an optimal operating point for sub-threshold operation. Okay, so the regular buck converter with cores connected in parallel is shown at the top, and the regular, or not so regular, cores stacked in series is shown at the bottom. The important thing to note is that we have to balance the current through each of the cores in the second system, but we don't have to balance the current in the first system. But the problem is that for the first kind of system, we have a fixed DC rail voltage that the core has to derive its current from, and that might not be optimal for our, that might not be an optimal solution if we want to use our advantage of sub-threshold operation. Like with activity factor of the cores, we might want to operate core 1 at a different operating voltage compared to core 2. This is possible if we properly manage the core voltages in the series connected series stacked system. And also the main important thing is that we have a like 0.8 volts output from at Vout, while we have some kind of, I mean, the buck converter will have very low, comparatively much lower efficiency, and also it will have to deal with much higher transients in the first case. And for this one, since the voltage output has been considerably increased by many times, and due to the averaging effect of the current, the output impedance requirement of the buck converter in the second case is much lower. So we can deal with transients much better in this case. Okay, so here's the basic uh, power management that scheme that we are planning to use if we have a stacked system. Like, first of all, the power drawn by the circuits, the CMOS circuits in between, we should first try to balance those powers in the software and firmware level. Hardware level means operating the DC-DC converters in between, so that will cause power losses obviously. And if we plan to integrate the converters on chip, then that becomes an issue. So the DC-DC converters will be only used as a last resort. So here we have the differential power processing scheme for voltage regulation of each of the nodes in between. This is the load-to-load configuration. So each of the converters, they deliver power from one of the loads, or power coming into one of the loads, and dispatch it to the next load. So that's basically the current law that is required so that the voltage regulation is maintained. Well, and if we operate the converters, all the converters in CCM, maybe forced CCM in some cases, then D1 prime will just be 1 minus D1. And if we don't consider that we need to operate each of the CMOS circuits at a different voltage, then we can simply operate at 0.5 due to ratio. Well, the advantage mainly for this one is that we can easily integrate each one of these converters on the board compared to the bus to load configuration, where each of the converters have a different switch voltage, and we have to deal with problems because of that. And this one has the added advantage that all of the voltage requirement of the switches are the same. So there's that. And main disadvantage is that we have a coupling we have coupling between the inductor currents. So as we increase the number of circuits, CMOS circuits in the series stack, this coupling sort of structure leads to some stability problems that we are going to see a bit later. Okay, so the model of the CMOS circuits, what I have taken is a resistive model because the power loss is basically capacitive, so it is proportional to VDD squared, and alpha is the activity factor that is proportional to the number of probability that some of the switches are going to switch from some of the nodes are going to switch from 0 to 1. That depends on basically what type of CMOS circuit are we using, and the frequency of operation, and the C is the net effective capacitance that is seen from the DC rail of the CMOS circuit. So the resistive model gives us that resistance of the core is 1 by alpha into frequency into capacitance, and alpha can vary between 0 and 1. The frequency is usually not constant, but usually it is not determined by the power management, and the capacitance is basically constant thing. So for this system, it might seem that it might look like a buck boost converter, but it is in all sense it is a buck converter, because we have like it is a synchronous buck converter. So and if we do the average analysis, then we will find that these two capacitances get in parallel, so we have an effectively twice the capacitance if the upper module was not present. So for controlling the for regulating the midpoint, this voltage at this point to VDD, I designed a compensator that works pretty well for high frequency switching, high switching frequency of 1 megahertz, and the inductance and capacitance values I have chosen such that the capacitance value is quite less compared to the usual capacitance values that are kept for power management of processors. I have this is because mainly we want to integrate the power converter, so this is still pretty high, but it's manageable. And the 500 nanohenry inductor is for going from -1 amps to +1 amps in like one switching period. So from that's my considerations in this design, pretty easy considerations. Okay, so for one of the worst case, for the worst case situation, I will have, oh wait, so I am assuming that I have VDD equal to 1 volt, and maximum mismatch current that the DPP converter has to compensate for is either goes from -1 amps to +1 amps. It does not mean that the processors are consuming 1 amps at 1 volts. It means that the mismatch is 1 amps. For simulating for a worst case situation is when the this inductor current goes from -1 amps to +1 amps, and this is the activity factor for change for that condition, and we obtain pretty good transient response, which is within 3% limit that is usually kept for processor voltage as a processor voltage requirement. We move on to let's add 2 more cores to the stack and see what happens if we can meet the same requirements as before. So over here, the first three of the activity factors are going down and the last one is going up. So this one actually denotes the worst case transient of this inductor current, which goes from minus 1.5 amps to plus 1.5 amps. And over here I have another of the worst case scenarios in which this inductor current is taking the worst case lift. For the first one, this one is like taking a leap from minus 1.5 to plus 1.5, and well, we can see that the voltage requirements is around, the voltage regulation is around plus minus 0.4%, which is still kind of within the limit. We can manage to get a better performance with this. And this is for the next transient case in which the middle inductor is undergoing its worst case transient. So here it is also within 4%. And now we move on to if we add 2 more cores. Okay, so before that, I have to inform you that we have like a mismatch dependent voltage ripple in this case. That's mainly because this one behaves like a buck converter, but this capacitor also sees some discontinuous current due to this inductor and this switch. So that discontinuous current will be maximum or will play a very big part in the ripple only when there is mismatch between the powers of these two resistors or these two CMOS circuits. So this actually causes some problem because we have to now decrease the crossover frequency a bit so that the noise does not creep into the control circuit, switching noise. So this gives us slightly slower response than we expected from when we designed the compensator for this one. Okay, so now getting to adding 2 more cores to the stack, we have first of all I have simulated the different worst case inductor currents and transients. Well, we see that it has become quite unstable compared to the previous 2 cases. That's because of the inductor current coupling, which is denoted by this matrix equation. To maintain our voltage requirements in this case, we have to increase the capacitance value. So for this case, I had to increase the capacitance to 40 microfarads from 20 microfarads and decrease the inductor value to 1/4 or half of the inductor value that I had before. So that gives me almost the same crossover frequency and kind of something like lesser noise. So this is the second case. Over here, the second inductor current is taking its maximum swing that may occur for this one, and still the voltage requirement is being met pretty good. And for this test case, The third inductor current, I'm simulating the third inductor current worst case, so this is also fine, but with increased capacitance, of course. Okay, so points to note are that if we have a transient at the middle of the stack, then it takes more time to settle down. That's because the transients have to go through all the converters that lie at the top of the uh, point where the transient is originating. So that causes uh, the system to slow down a bit for transients which are occurring at the middle of the stack. So, and another thing is that we have to decrease the coupling between the inductors somehow, because that if we decrease the coupling, then it improves stability. Okay, so this is one of the possible ways to decrease coupling. This is just the hybrid configuration, as someone has mentioned before. So we have this converter that is, you can all call it both load to load or bus to load. It doesn't matter because it is directly connected to the buses. And we have two internal converters for maintaining the node voltages at these two nodes, and two internal converters that maintains the node voltage as these two. So by reduction of coupling, I mean that whenever transient occurs at this node, these DPP blocks or converters don't have to work to uh, remove the effect of that transient. It will be taken care of by this block, and this block over here. So from this matrix equation, we can directly see that. So we have like a cross diagonal or tri-diagonal matrix over here and over here, and the middle one is just, I mean, decoupled from the rest of the inductors. So transient response, coming to transient response, uh, I will see a improvement in performance. So we see that the inductor currents are much more stable, because now the switching noises are playing much less part because of the decoupling of this upper portion and the lower portion. And for this one, I have just simulated the worst case transient conditions for the first inductor in this one, this energy DPP block, the second inductor in this DPP block, and the third one is this. So this is the first case when the first DPP block has to increase the current from the minimum value to the maximum value. So it's taking a leap from -1 to +1 amps approximately. And we can see that, I mean, this is regulated within 6% from this simulation, but I can increase the, but now I have the liberty to increase the crossover frequency so that I can actually improve the transient response by quite some bit. So it will fit in within 3%, within the 3% limit. And this is for the second one. Over here we see that it's jumping from +1 to -1 amps, the second inductor current, and more or less the voltage is within the 5% limit compared to it was more in the previous case. And for the last one, I am just the outer loop converter is going through the worst case transients from -1 amps to +1 amps. Okay, so reduction in coupling has improved my noise performance so that I can now move to a higher crossover frequency. But the main problem with this configuration is that these converters have a switch voltage requirement of 2 volts and these converters have a requirement of thrice that voltage requirement. So therein lies the problem, because it becomes more difficult to integrate the circuit. Okay, so now this is the second hybrid configuration, or we can call it the hierarchical hybrid topology. So over here, what we are doing is that we have completely decoupled the internal converters, so that, and the converters lying outside are coupled still. Well, the converters lying outside have a voltage of 2 VDD across its inductor, compared to 1 VDD in these internal converters. So the slew rate of the outside converters lying outside is twice of the converters lying inside. So we can handle we can handle coupling much better in the outer loop compared to the inner loop. So this is one of the main advantages of this one, and this topology. And we don't need, we have just managed to increase the switch voltage requirement by 2 times compared to these converters. So it's a possibility that it can be implemented in integrated circuits. For my future work, I have to consider some light load operation for the converters, because what will happen is that most of the time the software and the firmware is going to uh, balance the activity factors by quite some margin. So my converters might have to operate at light load configurations, or it might have to just DCM might not be fine with this kind of situation. We might have to move on to pulse frequency modulation or those kind of techniques. That has to be taken care of. And also another possibility is that we can consider, like, we are, with this topology, we are moving the transients at this node directly to the DC bus. So that is giving me a pretty good advantage for managing the transient response, instead of propagating through one converter over here and another converter which is connected here, and then again another converter which is connected to the rail. So this is something that we can focus on, and we can take some we can take a leap that if we couple the inductors in this in the center of the stack to the inductors which are at the extremities of the stack, then it might have a positive impact on the transient response, because in that case all the converters in the middle are bypassed during the transients. So that's one of the other possibilities that I'm working on right now. And also, for now, I have just managed to control 1 amp of mismatch current at 1 volt. So if we need to handle much more than that, then we can move on to interleaving of the converters. One very important effect is that if we operate in CCM, then the duty ratio is 0.5 and or close to 0.5. So if we couple the inductors and interleave them, then we can almost do away with the inductor current ripple. So that can be one of the possibilities if we want to move on to higher power ratings. Okay.
Do you do any like theoretical analysis, like coming up with kind of expression for how the fractional transits in relation to the position of the user.
I
That
have,
would be interesting.
yeah, that would be interesting, and also that would give us much insight. I have actually done that for a 3-core system, but moving on to an N-core system in general is going to be difficult.
Okay.
So let's
If
see.
you make any progress, let me know.
Yeah. Okay, any more questions? That's it.